You get lied to a lot. That's why you
because of its size.
Okay, so problem C, we're gonna do number 2 and number 3. Now, number 2 is actually quite easy. But again, it was not a math problem, so it freaks some of you guys out, but it is kind of a math problem because again, we learned yesterday that G is equal to G ME over R squared, right?
What does the E stand for in ME?
Earth. Or whatever is Earth for you at that moment.
So in this case, it's going to be Saturn. Now, what we said was, if you're standing on Saturn, and again, that's why I put surface in quotes, because it's a gas giant, so you just kind of sink down until you hit your density. It's not like you hit something solid in there. I mean, there might be something solid way, but who knows how deep you have to go before you got to that. Anyway, you would just kind of sink down. But if you could stand there on Saturn's surface, the acceleration due to gravity there is very similar to what it is here on Earth, even though their mass is 100 times bigger than our mass. And so I'm asking, why is that the case? Well, again, if we look at the formula like we looked at Newton's formula before, then this part obviously isn't going to change. But if their mass is 100 times bigger, but I want G to be the same, then what has to be true?
The radius has to increase the same amount.
Yeah, if the top got 100 bigger, then the bottom needs to get 100 bigger. But R is squared, so this R really needs to get 10 bigger to say that's going to come out to be about the same. So basically that's telling us, well, if the G is the same and they have 100 times the mass, then the radius must be about 10 times bigger than our radius, which is in fact what is happening. So Saturn has 100 times our mass, but its radius is only 10 times bigger, but then that ends up canceling out because that distance is squared. Get it?
That's the answer?
That's the answer.
What?
The radius must be 10 times bigger, which it is. Okay, moving on to C3. In C3, Sammy is trying to establish orbit over a planet. His ship sensors indicate that the planet's acceleration due to gravity is 3.21 times 10 to the negative 6 meters per second squared. So we got 3.21 exponent negative 6 meters per second squared is our G prime. We want to know how high above the planet's surface he's orbiting. If the planet radius is 159 gigameters, giga is 10 to the what?
6.
Giga is 10 to the what?
9. It's 9.
So that would be the same as saying exponent 9 meters. And the mass is 4.23 exponent 28 kilograms, and kilograms is what it should be. So that one we didn't have to change. So if you just look at the numbers, this gets confusing because you're saying, well, how high above the surface? You already have a radius. What's going on here? Again, if you draw a picture, a lot of times these things become a lot easier. He's trying to establish an orbit up here somewhere.
Of course.
And what we're calculating when we plug into this formula is we need this whole thing is our R. That was a beautiful bracket I drew there, right?
Yeah.
So that whole thing is going to be R, but the R I gave you here is just this R, and what I'm asking is how high. Hey, that's a better bracket. I'm asking for how high over the planet are we?
Yeah.
So what we have to do is we have to solve this equation here for R, and that gives me this big R, and then I have to subtract out this R to get me what's left over yonder.
Yeah.
That make sense?
Yeah. Okay, do number 4.
So if we're looking for R, then of course R and G are just going to trade places, so we're going to get R is equal to G ME over G times square root. And so we'll get that, so we're going to have the square root of, and again, big G is always 6.67 exponent negative 11. And then we're going to times the mass of the planet, which in this case is 4.23 exponent 28. and then we're gonna divide by T prime, which we said up at that height was 3.21 exponent -6, and we're gonna close the parentheses, and we're gonna get a number 7.79 exponent 11 meters. And again, that's going to be this whole distance right here. So what I need to do is subtract out this much of it to tell me what's left over here. So this much of it we already figured out was this radius. So I just need to take this minus 159 exponent 9 equals. Wait, what?
No, that's not right. It was for that one. It was 9.38. Exploded out.
You got what?
9.38. Exploded. 9.38.
Oh,
Yeah.
you would give me the final answer?
Yeah.
That's what I get for listening to you and not plugging in myself.
Yeah.
Dang kids anyway.
Yeah.
My apologies for those of you who are listening online. It's all Jerry's fault.
It's always Joe's. It's all TCO.
Well, duh. We know it's always Jerry's fault. Not like I could have made a mistake.
You made a mistake yesterday with the big K.
Okay, so if you plug this thing in properly, you should have gotten 9.38 exponent 11, and then if we subtract that out, then we get to 7.79 exponent 11
There you go.
meters.
That's
Yay!
No.
So, again, we're taking the equation, rearranging it for R, but the R is the total R, and all I was asking for was how about the planet, so we had to subtract out the planet's R. That's all it is, yeah.